So in 1959, some neuroscientists, Hubel and Wiesel, did an experiment in which they took a cat and they anaesthetized it. Don't worry, the cat was absolutely fine after the experiment, and healed quite nicely, and it's not as barbaric as it perhaps looks on YouTube, and you can find the video for it on YouTube. It's great. They took a cat and they took an oscilloscope, and you can see here they placed a single electrode to a single neuron in the striate cortex, the cat. And then they had a board with lights on it. And what they were looking for is to try and understand how neurons encode information about the environment visually. At this point, it actually already been known that light enters the retina. There's a layer of retinal cells that feed forward to bipolar cells and then onto retinal ganglion cells, and these then feed to a part of the thalamus inside the brain, and they cross over in the middle. Your left part of your left eye goes towards the right side of your brain and vice versa, by the optic chiasm, and hits your thalamus. A particular region of your thalamus called the lateral geniculate nucleus here, the LGN, and then onto the striate cortex. And they wanted to understand how striate cortex neurons are representing what they're receiving at the retina. Initially they didn't have much luck. That's because they were looking at single dots on the screen, and it wasn't until they were changing slides, bearing in mind this is 1959, that as they changed slide, the corner of the slide went across the screen of light, and it made a faint line, and the neuron was firing in response to that. And that's when they realised that neurons in the striate cortex are responding to orientation bars of light, not points of light. So the retina is looking at points of light, and by the time it gets to higher areas in the striate cortex, higher layers, you're getting more complex features like linear lines. And this led to a particular way of understanding how optics are computed in the brain. What it suggests is, initially, when you're looking at a linear line, the linear line is made up of points of light, these little cross bars which activate the retina. And as I was saying, in the retina it feeds forward to bipolar cells, a very thin layer of your retina, and then these bipolar cells synapse with retinal ganglion cells to create off-center surrounds. So that's what these smaller circles are on center, and then the surrounding area is off. And that's pinpoints of light. So retinal ganglion cells are detecting points of light. And these then feed forward to the LGN, and then from the LGN on to the striate cortex. And so recognize something quite important here, and that's that points of light at the retina correspond with points of light in the cortex, and this is what's called having like a map of the cortex of points of light. It's spatially coding. These neurons spatially represent space at the retina. This is called visuotopic mapping. And then these three neurons synapse together onto one neuron here at a higher region of the striate cortex, called the peristriate cortex. But because these three neurons synapse with this neuron, when this neuron fires, it's not representing single points of light, it represents an entire, it represents the summated input. So it represents this entire bar at a certain angle. So these kinds of neurons code for bars of different angles. So they all activate. These are orientation selective neurons. It's called a receptive field for particular angles, and this kind of predicts that the further you got the cortex, neurons are encoding for more complex items. And so when building Capuchi-Net, this Hubel and Wiesel model of visual biocomputation is what we took into account. And so for Capuchi-Net to recognize things, I mean, bearing in mind it's a simple neural network of only around about 255 neurons, we decided to keep things simple at the individual kind of pixel level, if you will. And so we used icons. I've actually drawn some extra characters in here just so it makes it more clear what these icons are meant to be representing in the environment. So each of these squares would be a pixel on the retinal ganglion cell. So like an on-center, off-surround activation of the retinal ganglia. So for a feeding platform, we've got like a rough square that's not filled in the middle. For the raptor, we've sort of got like wings and talons coming off here for the raptor, snake, capuchin, and felid. I still think this looks a bit too much like a giraffe. Something that we might change in future iterations of Capuchi-Net. So going on to Neuronify, and I must say at this point that Neuronify is an absolutely amazing application. I'd recommend it to neuroscientists, cognitive neuroscientists, and biological anthropologists, psychologists, cognitive psychologists, evolutionary psychologists, any of you guys out there. I'd really thoroughly recommend it. It's a great application because you don't need to get into the statistics of how a neural network works. This is a conceptual model, like a pre-model, before you then run it through something like you'd find on MATLAB. So it's absolutely fantastic, and I just wanted to say that at this point. But what we're seeing here is the retinal ganglion cells. We've got about 48 of these here. These then input to the next layer of this, the first layer of the striate cortex. And in this model, these are like linear bar detectors. So each of these three neurons would synapse with a single one of these. And so this enables Capuchi-Net to detect linear lines. And then you've got further layers of the cortex. And what these neurons are, these would be like visual area 4 neurons, where they're detecting collections of linear lines to identify more complex shapes. So from my memory, this particular neuron would be computing a snake head, this neuron a top right corner, this a top left corner, bottom right corner, left bottom corner. This would be a snake head in the left orientation. This would be legs of a terrestrial quadruped. This would be head of a capuchin or a felid. And then these synapse with these neurons here, which are sensitive to where in the visual field is the object occurring, and this is obviously important for Capuchi-Net to evaluate its spatial where it is in space. And then finally we've got the highest level of this visual area is the output here, and this is like a more semantic area. So this would be coding for categories of phenomena. So we've got raptor here. So if there's a raptor signal, which was remember the wings and the talons, if this kind of pattern appears on the retina, we'd expect this neuron here to be activated. And we can actually go ahead and test this now. By the way, the neural network is huge. It actually expands way above up the top here and down there. So if you don't see some activation, it could be off screen. But if we activate Raptor, these are inputs that simulate light hitting the retinal ganglion cells. So if you watch at the square here, you'll see the Raptor pixel confirmation. Raptor confirmation was activated. This should output some neurons here. You saw that one firing, and across here. And eventually, what we should see is Raptor neuron should fire. Just wait for it to flash white. It takes a while because it's such a massive neural network that my computer can sometimes struggle to compute it. It activated Raptor. It also activated Snake then. That's primarily because we can't... this neural network, with it being a conceptual neural network, it's very difficult to train it to modify connections once you've made the model. In fact, we'll try pressing Snake and see what happens then. For this button, we should see this neuron here, the Snake neuron, being the only neuron to fire. We'll give it a go now. So Snake confirmation hit the retina. A neuron in layer 1 activated. Neuron in layer 2. Now look at the final layers. There we go, only Snake neuron activated. We'll give Raptor one more go. You see the left Raptor wing actually corresponds to a similar feature found in the snake, so that could be why Snake's firing. Something that definitely have to modify in future iterations of Capuchi-Net if it persists. Yeah, it's activating Snake and Raptor again. That's something that can be modified in future iterations. See, a real-life capuchin would have had many experiences for natural selection to improve upon the templates innately, and also experience during the life of the capuchin, which would modify these connections, these synaptic connections, the weights of them, to other neurons, and that's something that's pretty much static when you're doing a conceptual model like this. But we'll have a go with platform input, and this is the neuron that should be firing. So I'm going to press platform. Saw platform confirmation, a square activate. So it's now in the second layer of the network, and we now look at the final layer, the output layer. There we go, platform has just fired. So that's correct. And we'll give Felid a go next. Felid confirmation in the retinal ganglion cells. Watching layer 1 now. We've seen 2 neurons fire in layer 1, some at the bottom there as well. Layer 2 neurons have just fired. Now looking at Felid. Interestingly, we're getting several responses here, so that might be something we need to look into in future as well. we'll give capuchin a try. I've got a suspicion that because I'm pressing these rapidly without giving much time between pressing them, another phenomenon that can happen in a neural network like this is it takes time after a neuron's been excited for it to return back to its ordinary membrane potential. And so if a neuron's fired, particularly these higher neurons that have inputs from several neurons, it means it can attenuate them and make them more likely to fire. So, I mean, we noticed for when we activated Felid, several of these fired off, and that could be the reset time problem. Give capuchin a go now. So capuchin in the retinal ganglion cells. Some layer 1 neurons have fired. Some neurons in layer 2. Now looking at the output layer. And only capuchin is fired there, which is what we predicted. So we're seeing that I gave it a longer break here with the reset time. So that could be the factor of what's causing this, and this is something I'll look forward to in future experiments testing this network, perhaps a future video. But a final point to make on Capuchi-Net is these output neurons here for representing raptor, felid, snake, platform and capuchin were precisely what we saw in a previous video I made on how capuchins interpret signals in different contexts. It was a video on cognitive pragmatics, and in that video I was talking about how single neurons can represent raptor, and I was referring to a visual part of the system, and this is the visual part of the system that interfaces with those neurons such that a single neuron can represent an entire visual concept. And so in future videos, once I've trained this network up a bit by testing it and making some modifications, I'll show how an association between an alarm call and this concept of raptor, for example, the bark alarm call and raptor, can be modelled using an artificial hippocampus. And it's going to take a while perhaps to modify this visual system. In fact, considering we've had a bit of a break to enable all the systems to reset, there's quite a lot of variables. For each one of these single units, like this unit, there's values for the membrane potential, the reset time, the conduction velocity in across milliseconds. There's the weight value, the threshold value, the activation value. There's many values, and so this is really slowing down my computer having this many neurons with this many different dimensions of value. So now we're going to try pressing Felid and seeing what happens now. So Felid confirmation, layer 1 neurons, there, yes. So only Felid fired then, and that's demonstrating that this network does work fine. It's just it's got a particular weakness, and that is if we have too many of these firing at once, at one time, it can overexcite the network and you get false positives. I guess the analog in that in nature would be something akin to having so many things to process that you kind of have a bit of a mental breakdown. I mean, the natural capuchin can obviously deal with this because it's got many hundreds of millions, perhaps even a couple of billions of neurons to deal with this. I'm only using at this point just under 255 neurons, so you know, go figure. I mean, I'll give you a look at the expanse of this network here. So that's the entire visual system right there. So it's quite a few neurons and dimensions of variation. The dynamics are supermassive. And that concludes our this run through the visual system of Capuchi-Net. And I'll show another video of this. The semantic part of the network would be here with the cochlea and etc. that I had in the previous video, and I'll do an upload of that and also the hippocampus system soon. Okay, thank you.